Hello, this is the, I don't know, I guess the fourth, hopefully the last. It's the last one of the background videos for our reenactment of the Ever Given grounding. And keep in mind, we are actually just using that as a way to demonstrate this program that we use in our training courses for marine navigation and weather, called qtVlm, and it shows some of the great virtues of that program. That's the unique features, and we've covered several of them, but there are many. And so let's start here. We want to look at the issue of the fact that we're in a very narrow channel, and there is and so we want to be sure that we've got our charts right. But there's a way to test that, and that is we go back to the rules of navigation from the Suez Canal Authority. And that is here. Oh, we looked at this. Okay. So another thing they have is depth profiles. And this shows you exactly what in the canal at certain areas. This is at marker 154.7. That's how they keep track of, it's like a mile marker, but they're kilometers from the top coming down from the north headed south. And this is 154. This is a point that the Ever Given went through, this point here. And so what we did was take a picture of this to be sure that our charts are right, because if we're going to do this detailed analysis, we have to be sure the charts are right. So we take a picture of this, then we go into here to about the right region and zoom way in like that and take a picture of this. Okay? Then I come here. Then what I do is overlay. Whoops, let me just see how this works. So kind of a poor man's demo tool here. Well, actually, maybe not. Well, anyway, it's InDesign. I couldn't figure out any other way to do this if we could. So, but the main thing is check to see that everything's consistent. This chart is with just a big zoomed-in picture of what we actually saw. Then this is a screen capture from the nav rules showing the relative soundings or depths, dredge depths, control depths. And then we just stretch that out to the two ends meet the land on these sides here. And these are the areas which are 0 to 9. The buoys are at 9 meters. And every skipper knows that. That's told as many places that these buoys are at the 9-meter depth. And you see that if I pull this aside. Let me find a buoy here. Okay, there's a buoy. And if I do let me do a depth contour here. This is 0 to 9. 0 to 9, right up to here. And then if I do, this is going to be like, I think, 9 to 11, where we want here, vector information, 9 to 11. Okay, so this is a water depth. These buoys, all along, up and down the channel, they're at 9 meters. Okay. Back to our picture here. Oop, not that one. This one. Okay, so the main thing we see is that when this chart, the chart that we have puts these dredging marks, the dredging control marks, right exactly at the right spot. And then what we can do now then is I made this little picture, this kind of little picture of the boat. And so the ship here. And there's the ship right at the water line. Oh, no, there's the water is up here. There's the water line. So there's the draft, 16 meters. This is the depth sounder reading 25 meters. The beam is 60, and the GPS is located 23 off the starboard side here. And the air draft I looked up somewhere for this ship is 45 meters. So that's sort of what it looks like. So then we can keep an eye on, or we can have a sort of an underwater picture of what happens here with this vessel, because it does get close to, you see here, if you look at the track is at various places it's close here, and at other places it's close. And we just want to see what effect that might have. And the effect is, let's look at that, and I have some notes on that. It's pretty well known, but But okay, so here's some notes on what's called bank and cushion. Now, this is the top view. That's like our view of the ship that you see in the earlier videos. It looks like that. And that's sure enough what it looks like from a plane. But if you're down at the actual water level, it looks like a dolphin, actually. I never thought about that, but it actually looks like a dolphin. And if I were a yacht designer, I'd probably know why it looks like a dolphin. Anyway, that's not the issue. But that dolphin shape, funnels in the water, you see, as it's going. Imagine the ship being stationary. Ship is stationary and it's in a river. So this river is running in here like this. And this river is focusing water in here, but the water cannot compress, right? It's non-compressible. So it's got to pile up. And when it piles up, it does a couple things. First, it pushes the bow out. There's an outward pressure on the bow this way with this extra pile. It's actually notable. You look at a side view of some studies of this. There's a foot, more than a foot higher water here, more than that. And so that also makes a hydraulic head that pushes the current down this way. But then, as that forces the bow out, here's the rotation point of the ships. They're normally at about a third of the way in from the end. And as it rotates in, actually not just ships, I think a 30-foot sailboat's probably the same way. It turns, when the bow goes out, the stern comes in. Now, when the stern comes in, this area here gets real small. And so you have here the water flowing in at a certain speed, and then it's got to come out of here. It's going to just pile up even more. And so that means that water has to go faster here. So it has to go faster in this narrow channel. And then here's a rule. Area 1 times speed 1, area 2 times speed 2. So this water is going faster. Then we come down to the Bernoulli principle, or the Venturi effect that makes airplane wings lift up. What happens is, when this starts going faster here, in other words, with like an airflow with a longer route has to go faster to get there. But anyway, here in our case, we're getting our current here is faster than up here, and that makes the pressure drop. So that relative to the environment here. And so this has this higher pressure up here with the water piling up. So this pressure is higher than this pressure, and this pressure is lower than this pressure. So what happens is you get two things working at the same time. You have this cushion effect where this is trying to push the bow out, and this suction effect is sucking the stern in. So that makes it difficult for the navigator. Gets real close to a bank. Or it doesn't have to be a bank. This could be another ship. Frankly, it could be another ship. And so here are some, you could look over this. These are some forces involved. Here's a picture that I got from an article of studying this in an Australian research paper. But it's not uncommon. Well, it can happen, right? It's not unheard of. I'd say not unheard of that to get in this kind of death spiral, getting too close here, and then having trouble. And what happens here, and in a sense, you have to steer towards the bank to get this bow going straight here. Now, there's another thing that can happen. Think of this as the bottom. You can have the bottom underneath the ship, underneath here. You can have the same sort of thing happen when all of a sudden this area narrows relative to what it was. Then this can suck this bottom down, right, like this, and that's called squat. And then that happens here. What is this? Where's the rule? I don't see the rule here. But the rule is that squat starts taking place whenever you're about, within 2.5 times of your draft. And this ship was 16 feet, and you're in water 16 meters, and you're in water 25 meters. So you're really susceptible to all these problems, I would guess. Again, I don't know about ship maneuvering. I'm just, looking at the basic things that are generic. I don't know about that particular case that we're looking at. But anyway, if we come back now and look at our case here, when we get something like over, so where is the case? We can look at, you can look at this and look at the actual data here. So you see this has got this is where the GPS was essentially on this line at this point. Now, where is this relative to the trouble? Yeah, this is maybe even it could well be that this is the start of the trouble, because you see it's close here, then it comes over here, and it's very close here, and then there's trouble. And but if you look at the situation here, in other words, it's looking like there could be bank and cushion effects that were involved in this event. What do I do to study this? See, and again, our data here, I believe, is precise. So when that is there on that line, I can then take here and put that. Which line is that? Oh, no, that's the dredged area. That's this line right here. So that would be a case of just about like this, right? Just about like that. So you see that you've got, and again, this is misleading. It's white. This should be considered this all blue. All blue. So here's where the bank and cushion's taking place. But if you look underneath here, you probably got some notable, when you start getting closer up like this, you're getting some notable suction, and it could be that kind of leans a boat over something, leans a ship over something. Anyway, so those are the two factors of a cushion, and let's see, did I want to do anything else here? The depth profile, bank and cushion, and the effect of the currents. We've done that now.